Hey everybody. Today we're integrating rational expressions using partial fractions. Remember that a rational expression is just one polynomial divided by another. Partial fractions lets us rewrite any such thing as a sum of simpler rational expressions. Things of one of these four forms. A constant over a linear term, a constant over a linear term to a power, a linear term over an irreducible quadratic, or a linear term over an irreducible quadratic to a power. Each one of these four sorts of things can be integrated without too much difficulty. Here's an example problem. Let's integrate 3x plus 8 over x to the fourth plus 4x squared dx. There's not an obvious antiderivative for this, and there's not a simple u substitution that's going to help us out. So what we're going to want to do is to rewrite that rational function using its partial fractions decomposition, and then integrate each one of those terms that we get separately. So our first step when we do partial fractions is just to factor the denominator. Here we have a common factor of x squared that we can pull out of the denominator. The resulting quadratic, x squared plus 4, is going to be irreducible. The easiest way to see that is by considering the discriminant of the quadratic formula, b squared minus 4ac. Here, b is 0, a is 1, c is 4, so that discriminant is going to be negative 16. When the discriminant's negative, you have an irreducible quadratic. Here's the form of the partial fractions decomposition. In particular, notice that I've viewed the x squared in the denominator as a linear term, x, to the second power, not as some sort of irreducible quadratic. The decomposition then is a over x plus b over x squared plus cx plus d over x squared plus 4. Now we get a common denominator, equate the numerators, and solve for a, b, and c. A common shortcut here is to use a convenient value for x to kill some of the terms on the right. In particular, when I use x equals 0, the terms with a, c, and d all go away. And I'm just left with 8 equals 4b, so b equals 2. Plugging this back into the original expression and expanding out to get rid of the parentheses, I'm left with this. I still need to solve for a, c, and d. Now, since these are polynomials on the left and right that have to be equal to one another, the coefficients of the like terms have to be the same. So just looking at the x terms, on the left I have 3 of them, on the right I have 4a of them. Just looking at the square terms, I have 0 on the left, I have 2 plus d on the right. And looking at the cube terms, I have 0 on the left and a plus c on the right. Solving those, I get a is 3/4, c is negative 3/4, and d is negative 2. So if I plug those back into the form for my partial fractions decomposition at the top of this slide, I get the full partial fractions decomposition. Here it is. Now, remember my goal is to try and integrate that left-hand side. So let's replace it with what it's equal to, and then integrate each of these 4 terms separately. Notice that I've broken up the numerator of the x squared plus 4 term to get 2 separate fractions, 2 separate integrals. Now, the first 2 of these 4 integrals are going to be very direct. I can just use anti-differentiation formulas. The last 2 we have to think a little bit about. The third one is going to use a u substitution, and the fourth one is going to end up being an arctangent. Here, the integral of x to the negative first is the natural log of the absolute value of x, and the integral of x to the negative second is negative x to the negative first. So let's tackle these last 2 derivatives, the 2 antiderivatives rather. The x dx over x squared plus 4 is going to use the u substitution, u equals x squared plus 4, because the derivative of that u appears as a factor in the integrand. The derivative is 2x. Solving it for dx, I get du over 2x. When I plug that in to the integral of x dx over x squared plus 4, I get x over u times du over 2x. The x's cancel, I integrate, and I get 1/2 natural log absolute value of u plus c. Taking out the u, replacing it with what it's equal to, 1/2 natural log x squared plus 4 and plus c. I'm leaving out the absolute value inside the natural log because x squared plus 4 is always going to be positive, because x squared is greater than or equal to 0. So taking out that third integral and replacing it with what it's equal to, 1/2 ln x squared plus 4, I get this, which simplifies very slightly. 3/4 times 1/2 is -3/8, or is 3/8, and then I have a negative sign. Now I just have to deal with the dx over x squared plus 4. This has roughly the form of an arctangent. In order to make it exactly in the right form, I'm going to factor 4 out of the bottom to get 1/4 integral dx over x over 2 squared plus 1. Now if I do the u substitution, u equal x over 2, I will have something of the form du over u squared plus 1. Overall, that integral is equal to 1/2 arctangent x over 2 plus c. So now I go back to the expression I have for the overall integral I'm trying to do. I take out the integral that I just found, integral of dx over x squared plus 4, and replace it with what it's equal to, 1/2 tan inverse of x over 2. Simplifying a tiny bit, I get my final answer. 3/4 natural log of x, absolute value of x, minus 2 over x, minus 3/8 ln x squared plus 4, minus tan inverse of x over 2 plus c.